I'm from IBM Quantum. I'm a software developer at IBM, and I sit pretty low in the stack, about as low as you can go before you're at the hardware. And I want to first start off by saying I'm not going to be presenting a language today, but I'll be presenting an abstraction that we hope to formalize in terms of a language moving forward. And that's why I'm here, is kind of to bring this abstraction to light. And Professor Chang had just introduced that, programming at the level of analog pulses that control the qubits in our quantum systems. You can take that off even. Yeah. Good.
Sorry. Okay, let's do that.
Great, thank you. So where was I? Exposing the programming of pulses at the level of an instruction set architecture or a virtual instruction set architecture, as we're trying to do in Qiskit, so that we can target a variety of different quantum computing technologies. And so, earlier there was a mention of circuits being relatively low level, and I kind of, I have news for you, is that there's stuff underneath that, like that Tina was mentioning, the whole layer of abstractions. So we're going to go a step lower, and unfortunately this means we have to step into the physics a bit of how these quantum systems work. And I hope you'll bear with me a little bit as we move into the realm of physics. So, the core of what I want to speak about today is taking a quantum circuit, which is represented as a list of unitary operations, gates to apply to our qubits, and then projective measurements, and then decomposing it either through a kind of a naive lowering procedure from individual gates to pulse elements, or you might be able to do something like aggregating instructions and using optimal control techniques like Professor Chang was discussing to combine operations and design pulses on the fly. And from the ground up, this is how we've been trying to enable this with that sort of optimization in mind. So I'm going to focus on superconducting qubits because that's what we use at IBM. So what is a superconducting qubit? Well, we use transmon qubits, and you can think of it as a parallel LC oscillator where we have a big capacitor and then a nonlinear inductor, which is known as a Josephson junction. And this is going to form an anharmonic quantum oscillator. And what I mean by anharmonic is the difference between the 0 and 1 energy levels and the 1 and 2 energy levels. There's going to be a difference between these two. So this means that when we send in a stimulus pulse to the qubit, we're not just going to excite all the way up the ladder. We're not going to scale the ladder, but we'll be able to focus on the 0 and 1 subspace and use that as our qubit. And it's important to note that there's this transition frequency or energy associated with the 0-1 transition, and this is kind of where we'll target our pulses. So they'll have a carrier frequency around that frequency. So, sorry, let me restart this because it's fancy graphic time. And I really like this visualization because it helps us think about how a quantum program moves through a modern quantum computer and think about the various components in that quantum computer. So a programmer is going to specify a program in the circuit model, and it's going to be transmitted to the control electronics for the quantum computer. This may be heterogeneous hardware, but we're focusing on miniaturizing it, and then that's going to be translated to pulses, microwave stimuli, that are going to go through the measurement and signal chain in the fridge and interact with the qubit. And if it's a measurement, for example, that pulse will then travel back out of the fridge and back through the electronics, where the electronics will say, this is a 0, we measured a 0, or we measured a 1, and then that result has to get sent back to the user at the end of the day. And of course, we talked about closing the loop between a quantum computer and a classical computer, QRAM, et cetera. So, moving forward, there's a lot of miniaturization efforts, defining hardware ISAs that will have a classical component that interacts with the quantum component. So there's a lot of work going forward with this, and it's on the border of quantum computer engineering and computer engineering. It's a very exciting field. So if we think about the hardware involved in these systems, well, we have signal generators that are going to output a carrier signal. We have arbitrary waveform generators that allow you to specify an arbitrary pulse envelope to be played out in the device. And then we have mixers which take these and put these together, mix them together, and then send them down to the fridge, where we'll have a bunch of other hardware components we may or may not need to control, like amplifiers, splitters, coaxial cables. Of course, one of the main hardware engineering efforts is miniaturizing everything involved in this. So, at the end of the day, we specify a pulse envelope, we specify a carrier signal, which is going to be defined by a frequency and a phase, and we mix these together, and this is what interacts with the qubits. So like I said, we used superconducting qubits. We have single junction transmons. They have a frequency of around 5 gigahertz and an anharmonicity. That's the difference between the 0 and 1 energy level transition and the 1 and 2 of around 300 megahertz. And then they're all coupled together with coplanar waveguides with a frequency of around 7 gigahertz. And there are also measurement resonators that interact with the qubits that we can send stimuli down to the resonator, and this will weakly measure the qubit over time. So let's go through how a pulse will allow us to control a qubit. So we send a pulse in this case it's going to be a Gaussian pulse envelope at the frequency of the qubit, and it will have some duration, amplitude, and sigma, standard deviation to that pulse. And if we choose all those just right, we go through a very intense calibration procedure, we can excite the qubit from the 0 to the 1 state, or for that matter anywhere else on the Bloch sphere if we use if we optimize a different pulse. And now you might be wondering, why should I care about this? This is all very low level, and it's not, it's might be kind of too low level. But there's two reasons I'd say. The first one is that by standardizing these techniques and these abstractions, we're providing the tools to bootstrap a quantum system into a quantum computer. So a large number of quantum systems will be defined by this model. And if we standardize the characterization, verification, validation, and calibration techniques within this model, then we'll make it much easier to take a quantum system and elevate it to a quantum computer. And the other reason is that in the near term, we have a lot of constraints in our systems. We have high gate and measurement errors, limited hardware gate sets, limited in the number of parallel operations we can perform. And of course, there are hardware solutions to this. But as Professor Chong was alluding to, there are also a lot of software solutions to this problem. We can look at better measurement calibration techniques, pulse shaping techniques, different scheduling techniques. Like when we play out a pulse, say if 2 qubits are coupled together, you might not want to do an operation on both qubits in parallel because there would be crosstalk between these qubits. And so by opening up these sorts of optimizations within this abstraction, we enable new research into these techniques. So pulse programming, we're providing it as a kind of like an in-memory implementation of the language. We haven't defined the language yet, but we've defined a suite of instructions and an abstraction for how this program will interface with a quantum machine. And it's done within Qiskit. Qiskit is open source. We try and at IBM, we try and do everything open source, so it's available on GitHub, and you can go ahead, pip install Qiskit to get started. And there are 4 components within Qiskit. We have Terra, which is the foundation. It allows you to program quantum computers at the level of QASM or circuits or pulse. And then there's Ignis, which is a QCVV framework. There's Qiskit Air, which is a high-performance simulator framework designed to interact with Terra. And it will be releasing a pulse simulator to go along with the already pre-existing simulators. And then there's Aqua, which is the applications framework. So today I'm going to be focusing on pulse programming in Terra, and then we'll use Ignis to perform an example of how we might build a pulse from scratch and use it to do something of use. So how do we represent pulse programming in Qiskit? Well, we represent a pulse, the envelope of the pulse, as an array of complex valued amplitudes or samples. And we say that each of these samples is going to play out for a cycle, a unit of time dt, on a given channel that it's scheduled on. And when this pulse is played, it's going to be mixed up with a carrier signal with a defined frequency and a phase. So here we see kind of a diagram of this abstraction layer, where we say that pulses are scheduled and other instructions are scheduled on channels. They're mixed up with a carrier signal, which can also be, this carrier signal can also be controlled with instructions. And then they're going to interact with the system. And we also allow the ability to schedule the measurement stimulus pulses. And then we say that we can also measure our qubits, and we provide instructions to directly schedule the absolute timing of these measurements. So all instructions in Pulse have hard real-time deadlines. We can schedule them absolutely. And this is very important for composite gates. So let's think about it from like an instruction set architecture perspective. Well, in Qiskit, we can target not just superconducting qubits, but we hope to target a variety of other technologies. So we're really more at the level of a virtual ISA. So if we think about like the end goal quantum computing stack, we're going to come in right down here and provide access to the direct waveform controls and readout controls. And I want to stress that this model in general applies to pretty much anything that obeys the rotating wave approximation. At the end of the day, what ties the instructions we schedule to a quantum system is a Hamiltonian, and we define our instructions in terms of this Hamiltonian. So of course we can target our superconducting qubits, but we can also target semiconductor spins, quantum dots, NMR, ion traps, neutral atoms. We want to build a suite of general routines that will allow us to bootstrap these devices and enable research into these devices. So let's return to this initial diagram I showed you, and we can think about how we lower or naively schedule a quantum circuit into a pulse schedule. Professor Chong showed how you can take something like this and compress it, but that's kind of a more advanced technique that will be enabled and could be implemented within Qiskit quite simply. But just doing a more advanced optimization of these pulses on the fly in conjunction with knowledge of the underlying device. So if we look at our Hadamard, it's going to be decomposed into a pulse on the drive channel for 1 qubit, and then an associated change of the carrier signal frame. And then the CNOT is going to be a much more complicated composite pulse. There'll be pulses on the drive channels of both of the qubits that are involved, the control and the target qubit. And then there'll also be pulses on an interaction channel that's going to perform what's known as a cross-resonance pulse. And finally, I should add that this circuit is a Bell state preparation. Then we have to measure our qubits at the very end, and measurement is done with a pulse as well. And so this pulse is going to weakly interact with the qubit over time through the measurement resonator on the device. And then it's going to travel back out of the fridge into the electronics, where it will be sampled and discriminated into a state, 0 or 1. And so this is in the control of your this is in your control within Pulse as well. So this might seem a bit complicated, but within the Qiskit compilation pipeline, it's relatively simple. So we first specify our quantum circuit that we want to run, and then we have to transpile it to the native gate set. But of course, you can define your own native gate set within Pulse. So it doesn't just have to be your normal U1, U2, U3, CNOT, or whatever gate set you choose. And then you can schedule it into a Pulse schedule that can then be run on the device to implement the same logical circuit on the far left and get the same results. Of course, within Qiskit, it's a Python API for programming quantum circuits. So it's very simple in the quantum circuit model. But if you want to do this directly within the Pulse model, well, every quantum circuit instruction corresponds to many Pulse instructions. So we have to do things like define the actual Pulse envelopes that we want to play out, and these will typically be calibrated in a calibration routine. We have to define things like frame changes or acquisition statements that we want to schedule on the device. And then we can build up our circuit from its components. So we build up a Hadamard a pulse schedule, a CNOT pulse schedule, a measurement pulse schedule, and then at the very end we can append them all together, concatenate them to get our final pulse schedule, which is going to really be a list of instructions that are going to play out on the device. So now I'm going to dive a bit deeper into the physics, what I'm going to show is how you can use Pulse to calibrate your own CNOT gate and get comparable performance to the CNOT operations on our device with very little effort, thanks to kind of the power that Pulse has enabled us. So the CNOT operation in our devices is really quite conceptually simple, but the underlying physics is quite sophisticated. So the idea is we have 2 qubits, and they're statically coupled together via a resonator. And this gives us a ZZ type coupling. And if we pulse on the control qubit for our CNOT at the frequency of our target qubit, it's going to give us a Hamiltonian that looks like this over here. And we see that there's going to be a ZX term in this Hamiltonian. And if we choose the pulse for the right amplitude or the right duration, we can get a pi/2 rotation. We can obtain a perfectly entangling pi/2 rotation. But there's also going to be these other unwanted terms due to the physics in the device, as well as crosstalk in our actual devices. So if we think about this, let's play out a pulse on our control qubit. And depending on the state of the controlled qubit, whether it's in the 0 or the 1 state, we're going to rotate in a different direction around the x-axis. So with pulse, we can go ahead and do this. So now I'm going to show how we build up a cross-resonance gate in our system. So first, we define a Gaussian square pulse with some duration, amplitude, sigma, and rise-fall time. And then we schedule it into a pulse schedule. And then we can add this pulse schedule as a cross-resonance gate into our instruction schedule map, which relates circuit instructions to pulse schedules. And then we can use this cross-resonance pulse now as a gate within the circuit model. And then we can use the Ignis quantum process tomography module to generate a bunch of state preparation and measurement basis circuits, and run this through the Qiskit transpilation framework to optimize these circuits, and then schedule them on the device and execute these pulse schedules on the device. And then we can pass these results back to our quantum process tomography fitter and extract these states, the quantum channels that we're trying to measure for our cross-resonance gate. And so then we can perform Hamiltonian tomography in Ignis, and we can see the terms in our cross-resonance gate. And we see that, as expected, we have a strong ZX interaction, but we also have all these unwanted terms here due to the physics of the cross-resonance gate and crosstalk. And typically, we get rid of these using an echoing procedure in the standard gate that's provided to users in Qiskit. So we break up that pi/2 pulse and make it 2 pi/4 pulses with opposite directions, and then add an echoing pulse to remove a lot of these terms here. But what we said is, well, the ZX, the pi/2 ZX gate is a perfectly entangling gate. So maybe we can just add a bunch of pre-rotations and post-rotations, and then locally optimize all these local rotations by the parameters that define them. So we have 12 angles that define the U3 gate added before the experiment on both qubits and after the experiment, and just run that through a numerical optimizer and generate a CNOT schedule, an ideal, and try and map our channel onto an ideal CNOT with these local operations. And then we did this, generating the CNOT schedule here, and then we can characterize the fidelity, average gate fidelity of the schedule we defined through local optimization, our CNOT gate, as well as the one provided by the backend. And we do very well. They have comparable performance. And I should add that we tuned up the amplitude for our pi/2 gate in a very rough manner. So it's just an example of kind of how you can have access to performing research on optimal control techniques, on some of the biggest and highest performing devices in the world within Qiskit. And so there's still lots of work to be done. Like I mentioned, we have a chasm, a language that's kind of near an instruction set for quantum programming in the circuit model, but we don't have its equivalent for pulse programming. This is something that we want to work on, and we will be adding to Qiskit. And maybe these can be defined side by side. We need to identify this necessary instruction set. Right now, we're able to play pulses, change frames, schedule measurements, change the frequency of carrier signals. But there might be other aspects of devices that are general that we wish to incorporate. And then we want to standardize the compilation pipeline, pass manager-based scheduling. And we also, at the end of the day, there's physical hardware that's often quite different from quantum computer to quantum computer. And we want to standardize some of the constraints that exist in this hardware. Maybe waveform memory is different between hardware, or you have to align pulses at a different number of sample boundaries and alignment boundary. So we want to standardize the description of these quantum machines at this level. So if you want to try it out, you can access a quantum device with pulse level control at quantumcomputing.ibm.com at IQX. And we also have a lot of education resources. It's something near and dear to my heart because I think pulse could be a great education resource from the perspective of optimal control and quantum computing engineering. So thank you very much.
Right, we are a little bit short on time, but we'll have one quick question here.
So if I do acquire, do I get IQ values that I can write my own classifiers on top of?
Yes, absolutely.
Okay.
And we also support the ability to return the raw mixed down samples that have actually been measured on the device, but the bandwidth requirements for something like that is huge, so we haven't enabled it publicly.
All right, so in order, so our next speaker will do a little adjustment here. So the